Hello, my darlings. This is a huge day. We're going to look at the fundamental theorem of calculus. Remember, fundamental. That's like the basics, the building blocks of calculus. That's how important this theorem is. And it comes in two parts. We're only going to be able to look at the first part today. So here we go. Let's start with, if f is continuous on the closed interval from a to b, then the function f of x, capital, notice it's a capital F of x, so case is important. Capital F of x equals the integral from a to x of f of t dt, has a derivative at every point x in that closed interval from a to b. And not only that, but that derivative f prime of x is simply little f of x. Wow. So the fundamental theorem of calculus part 1, which we'll abbreviate FTC, 1, says that the definite integral of a continuous function is a differentiable function of its upper limit. So the key here, this is what's given to us, okay? And it's very important that this lower limit is a constant. That must be a constant. If it's not a constant, this is not going to work, okay? So that's really important. Now we're going to prove this. I know I don't do a lot of proofs, but we're going to do this one. So we're going to use the definition of derivative to prove this, okay? We know, let's remind you what the definition of derivative is, shall we? So the definition of derivative, I'm going to use it for capital F of x, is the limit as h heads to 0 of f of x plus h minus f of x all over h, right? And that's the same as df dx, same thing, okay? We also know that this is our given, f of x is the integral from a to x of f of t dt, okay? So that means that our df dx, or our f prime of x, is going to equal, now I'm going to take this f of x plus h and I'm going to substitute it into here. That would be the integral from a to x plus h of f of t dt minus, now f of x is just this, the integral from a to x of f of t dt, and we're back to all over h, okay? And we're going to do a little bit of manipulating here. So this, I forgot my limit. Yell at me. The limit as h heads to 0. Okay, so this equals the limit as h heads to 0 of, I'm going to keep the first integral, the integral from a to x plus h of f of t dt. But notice this a is here and this a is here. We want to use that to link these two integrals and make one integral. So I'm going to reverse it, which means I'm going to have to change that to addition. I change the sign when I reverse the limits. And now I'm still all over h. So now I have the limit as h heads to 0, and I can add these two integrals. When I add them, I get the integral from x to x plus h of f of t dt all over h, okay? So this is the same as the limit as h heads to 0 of 1 over h times the integral from x to x plus h of f of t dt. Now, by the mean value theorem for integrals, 1 over h times the integral from x to x plus h of f of t dt has to equal f of c for some c between x and x plus h, right? We learned that in the average value lesson. So that means that our derivative, df dt, because remember this is so far our derivative, this is the limit as h heads to 0, and we're going to take all of this, right, has to equal f of c. Oh, I forgot my 1 over h. Where x is less than equal to c is less than equal to x plus h. Now, As the h heads to 0, we can use the squeeze theorem right? As the h heads to 0, that will mean that the c has to head to x, because as this heads to 0, it's going to be trapped between x, and c is going to head to c. So then we're going to have capital F prime of x is this limit as h heads to 0 of 1 over h. F of c is the same thing as f of x. Yay! Now you've done the proof, okay? The proof is harder than the theorem and harder than actually using it. Using it is not so bad. Okay, so the Fundamental Theorem of Calculus Part 1 says that the derivative with respect to x of the integral from a constant to x of f of t dt is f of x. Okay, it means that every continuous function f is the derivative of some other function. Every continuous function has an antiderivative. And here it is, the process of integration and differentiation are inverses of one another. How huge is that? Integration and differentiation are inverses of each other. So that when we take the derivative of this integral from pi to x of sine t dt, notice that pi is a constant. When we take the derivative with respect to x, the integral from pi to x of sine t dt, all we get is this function evaluated at x. That's it. I know, you're sitting there going, that's way too easy, Mrs. Williams. You're not trusting me. I know, I hear it. All right, so let's find dy dx. Let's try a few more. We have y equals the integral from negative pi to x of cosine t dt. Well, the derivative of y is dy dx. We would have to take the derivative of the other side. Now, I'm writing it out the first time. I am not going to need you to write this step all the time, okay? It'll be okay if you come right down to this step. When we take the derivative of this integral, we're going to take the x and we're going to plug it into this function, and our derivative is cosine x. All done. So let's look at b. Y equals the integral from 0 to x of 1 over 1 plus t squared dt. So we take the derivative of y is dy dx. Now we're going to take this x and we're going to plug it into this function, and we're going to have 1 over 1 plus x squared. That's it. Let's look at this one. Y equals the integral from 3 to x of 1 over 1 plus t squared. So the derivative of y is dy dx equals, and we're going to take this x and we're going to put it in for t, 1 over 1 plus x squared. Now wait a minute. These are the same things, aren't they? Now, we know that different functions have the same derivative because derivatives of constants would be 0, so it's very easy to have multiple functions that have the same derivative. We're going to take a moment here and we're going to pause and go use our graphing calculator, the TI-Nspire, to look at how changing the constant in the integral changes the value by looking at the graph. So first we're going to look at how changing the constant, notice here it's 0 and here it's 5, when we change it when we're taking the derivative of an integral, how that affects the graph, and how it affects the graph if we're only doing the integral. Okay, let's go take a look. Okay, so here we are on a graph page. Now the first thing we want to look at is the derivative with respect to x. So I'm going to use my template key, and I'm going to use my derivative with respect to x of, so I'm going to tab, and now I want to do the integral. So we're going to do the integral from, and we're going to use the constant 0 first. 0, tab up to x of, and we're going to tab, and we're going to use the function x squared, but we're not going to put in x's, we're going to put in t's because you don't want to use x twice. So we're using a different variable. Tab and then another t, okay? And then I'm going to arrow down. Notice there's the graph. Notice it is just the function x squared. Oh, because I clicked, I got out of it. Now I'm going to go again, my template key, my derivative with respect to x, tab of, and I'm going to use my template key. I'm using the integral this time, and now my lower limit is 5, tab, we're going to x, tab of, our function was t squared, tab, dt, and we hit enter, and lo and behold, they're the exact same functions. So changing that constant as the lower limit does not affect the value of the derivative of the integral. That's cool. Now, what happens though? I'm going to add another graph page. So Control Doc, add a graph. What happens if we change the a in just the integral? So let's just look at the integral from 0 tab to x of tab t squared. So now we're not taking the derivative. We're just looking at the value of the integral. I'm going to tab over. This is dt. So that's what I would get. Okay, my function looks like this. Now let's go back up. So I'm going to tab up. Now I'm going to use my integral again, only this time we're starting at 5 tab to x tab, and my function was t squared tab dt, and we hit enter. Uh-oh, I can't even tell what that is. So I'm going to go to Menu, Windows, Zoom Out. There it is. They're very similar graphs, but it's been shifted down, okay? So it's been shifted down. The y and the x-intercepts have changed. They're the same shape, but it's been a translation down this time, okay? So it does make a difference. The lower limit being a constant, that constant is different when you have just an integral, but if you take the derivative of those integrals, it does not affect the value when you change that lower limit. Okay, back to work. Now let's take a look at this example. Let's find the derivative with respect to x if y is the integral from x to 5 of t sine t. So we have dy dx would be the derivative of the y, is going to be the derivative with respect to x, the integral from x to 5. And there's a reason I'm rewriting it this time. Is this in the proper form? No. My constant is up there. I need it on the bottom. So we would have to reverse the integral, but when we reverse the limits on the integral, we have to negate it. And a negative is a constant, so it can factor outside the derivative. That also means that in the future, you can skip this step and jump right to the one that I'm writing here. Okay, because now we know that dy dx is the negation, and we're going to take this x and we're going to plug it into the function x sine x. And that's it. So dy dx is negative x times the sine of x. So if the constant is at the top, you need to reverse the integral, but don't forget to negate that when you reverse the limits on the integral. Let's look at the fundamental theorem with the chain rule. Okay? Now there's two ways to do this. I'm going to do it first in a way that looks a little strange with u's, because I want to introduce u's to you, because later on u's are going to become important to us. So I want to at least introduce you to the concept of a u substitution here. So let's find dy dx if y equals the integral from 1 to x squared of sine t dt. Now notice we have a constant down here. Good. But this is an x squared, not an x. So we're going to let u equal x squared. That means then that y equals the integral from 1 to u of sine t dt, right? Now, if we use the chain rule, the derivative of y with respect to x would be the derivative of y with respect to u times the derivative of u with respect to x, which would be the derivative with respect to x of the integral from negative 1 to u of sine t dt times du dx. Well, even though this derivative looks scary, it's the same thing. We have a constant at the bottom, we have a variable at the top, we're going to substitute it into our function. We have the sine of u. And we still have du dx. Now here's the catch. What the heck is du dx? So we're going to come over here for a minute. if, remember, we said that u was x squared. If u is x squared, then the derivative of u with respect to x, the derivative of x squared, is 2x. So that means we can rewrite this dy dx here as the sine of u times, and du dx is 2x. Now the other thing we also have to remember is we don't want a u in there. I'm going to write the 2x up front so it doesn't look like my angle. And sine, but what was the u? U was x squared. So here is our answer. Now there is a much easier way to think about doing this. Okay, what we just saw is that if we have this function f of x equals an integral from the constant a to some function of x, in our case x squared, of f of t dt, then the derivative of our capital F prime of x is f of g of x. So we're subbing this into the function inside, times, do the chain rule, the derivative of the upper limit. Okay? Chain rule rules everything. So let's try this. It's not as bad as it sounds, okay? We have y equals the integral from 1 to 3x to the fourth cosine t dt. So the derivative of y is dy dx equals, and we're going to take this 3x to the fourth, gets substituted into our function, so it's the cosine of 3x to the fourth, times, what's the derivative of 3x to the fourth? 12x cubed. And we always put that in front, right? Standard form? Good. So some people like to do the derivative first. That's fine. Doesn't matter the order. So the next one, y equals the integral from 5 to 3x squared of sine t dt. So the derivative of the y is dy dx equals, we're going to take this 3x squared, substitute it into our function, so it's the sine of 3x squared times, what's the derivative of 3x squared? 6x. See, this isn't so bad, is it? You thought it was going to be horrible. All right, and then of course I give you one that's a little trickier. Now remember, we have here y equals the integral from 0 to x cubed. So remember, that's really the integral from 0 to x to the 1/3 of cosine t cubed dt. Okay, so when we take this derivative, dy dx, we're going to take this cubed root of x and substitute it in for t, so that we have the cosine of the cubed root of x being cubed times, now we have to take the derivative of the x to the 1/3. Now the derivative of x to the 1/3, we bring down the 1/3, keep the x, subtract the 1 from the exponent, that's negative 2/3. So now if we neaten this up a little bit, dy dx is going to be 1/3 x to the negative 2/3 times the cosine, and when you cube a cube root, you're just going to get x. You could rewrite this. I'm okay if you give me this. You could, if you wanted, rewrite this also as the cosine of x over 3 times the cubed root of x squared. That is also the same thing. But like I said, I'm okay if you stop here for these. All right? Now, this one, what's wrong with this one? My constant is at the top. So we're going to negate it and reverse this. So it's the integral from 5 to x of 3t sine t. So now, when I take my derivative of y, it's dy dx equals, I keep my negative. We're going to substitute this x into the function. So it's 3x sine x times the derivative of that upper limit x is 1. So we're done. All right, one last one. One last problem. Take a look at this one. Uh-oh, there's no constant. This is y equals the integral from 2x to x squared of 1 over 2 plus e to the t dt. And I told you, in order to use the Fundamental Theorem of Calculus, part 1, your integral has to start at a constant. Does that mean we can't do this? No, it does not. It means we are going to pick any constant you want. I'm going to pick 0. You can pick any one you want. I'm picking 0. And I'm going to rewrite this as y equals the integral from 0 to the old upper limit x squared of 1 over 2 plus e to the t dt plus the integral from the lower limit 2x to that number that I picked. It doesn't matter what number you pick as long as it's here and here, okay, of the same function. All right, because when I add those two integrals, I will get the original one that I was given. Now I do have to do one more thing because we do need our integral to start at a constant. So my first integral does, that's okay, but my second one doesn't. I need to reverse it, which means I have to subtract the integral from 0 to 2x. Now I have constants on the bottom of both, and I'm going to plug the x squared in. So my derivative of y is dy dx. I'm going to substitute in that x squared, so it's 1 over 2 plus e to the x squared times, what's the derivative of x squared? That would be 2x. Minus, now this time I'm going to substitute the 2x in. So it's going to be 1 over 2 plus e to the 2x times, what's the derivative of 2x? 2. So I'm just going to change that 1 to a 2. And now I have my answer. And there you go, guys, the Fundamental Theorem of Calculus, Part 1. That the derivative of an integral evaluated from a constant to a function of x is just that inside function evaluated at the upper limit times the derivative of the upper limit. All right, guys, see you soon. Bye.